Hey guys, Mr. Nazarevich here, and today we're going to be looking at an introduction to sampling distributions. So this is one of the more abstract concepts in AP statistics, and today's going to be an introduction. So here are all the students from the 2020-2021 AP statistics class, and as you can see, I've got them in alphabetical order, and I looked at the number of letters in a student's last name. So for example, Gavin Connor, let's see, has 6 letters in the last name, C-O-N-N-E-R. So you can find yourself on the list. Now, there's 57 students total, and the distribution of the data looks like this. So, as you can see, there is a right skew to the distribution. The distribution is skewed to the right with a mean of 6.263 and a standard deviation of 2.2. 3 of the people would be considered outliers. Let me do 1, 2, 3. Now, imagine that we have this population, but instead of 57 people, each dot represents 10,000 people. So there's going to be 10,000 people that have 14 letters in the last name, and there's going to be 20,000 that have 9 letters to the last name, etc., etc., etc. So it's a pretty big population. It's 57,000 people. Nope. Yes. Is that right? Not 57,000. 570,000 people. Yeah, 570,000 people. So a little bit more than 500,000 people. Now, let's say that I select a random sample of size 10 from the data set. And since each of the dots represents 10,000 people, I'm going to be sampling with replacement. So I'm going to go to random.org, which is something we can do. Let's see. I'll show you the process of selecting a sample like that. So let's go to random.org. You're going to have to do one of these later on next week. Go to numbers, integers, generate 10 integers between 1 and 57 in, let's say, 5 columns. Get numbers. So there would be a sample. So that's how I generate a sample. All right, so for this example, here were my numbers, and then I went back, and so for example, 26, if 26 gets selected, I'll look at the 26th person, that's Mason Esworthy, and Mason has 8 letters in his last name. So the 26 here would correspond with the 8. Now the 38th person, that is Annette, and she has 14 letters in her last name. So this 38 corresponds with this 14, etc., etc., etc. Now what I'm going to do is I'm going to find the mean for our sample. And I'm going to denote that by x bar. So x bar is a sample mean. Compare that to mu, which is a population mean. All right, so my x bar here is 7.3. Now, notice that's just one random sample. I can find another sample. Same idea. Here's my new sample. Once again, I can see Mason's in there. Wait, no, that's Annette. I think, yes, that's Annette. The 55th person, let's start with that. That would be Sam. And then in my next sample, the 33rd person would be Anna, etc., etc., etc. So different random sample, different mean. So you can see that pretty much any sample that I do is going to have a different mean. Now, in this case, both our samples ended up having means that are larger than the actual mean. Part of it is the fact that, I mean, there's just luck involved in that. And if I'm picking a smaller sample, a sample of size 10, if I get an outlier, then that's going to have like quite a big impact on the sample mean. Now, what if instead of a sample of 10, we did a sample of size 30? Once again, I would generate 30 numbers. So here, instead of 10 numbers, I would generate 30 numbers. Get the numbers. There's 30 numbers. I would go through the whole song and dance of matching up each of the numbers. So 55, I think we said is Sam Walker. And now I take a look at my sample, and I find that the mean for that sample is 5.967, which is a lot closer to the 6.2, what was the population mean? 6.263. Now, I expect larger samples to approximate the population mean more closely. So, our sample is a lot closer to the population mean than either of our samples of size 10. In general, the larger sample size, the more likely it is that our sample statistic will be closer to the population parameter. So the population parameter is the thing that we would actually know if we took a census, but oftentimes a census in a large population is impractical. So we have to take a sample. Now, Colin Michael is a former student, exceptional stats student, math student in general. He wrote a program that allows us to generate large samples of different sizes. So I asked him to, I asked him to generate like 1,000 samples from our population with replacement. And then he did samples of size 10, 30, and 100. So, same idea. We look at a, let me see if I can, basically, here are 1,000 samples of size 10. Notice it has a slight right skew to it, and the range is a lot tighter than our population range. So our population range of our actual population goes from 3 up to 14. When we did 1,000 samples of size 10, we ended up going from roughly 4.5 to 9.5. Now, and this is like a sample of size 10. I find the mean. I do that again and again and again until I have 1,000 of them, and then I plot all of it. Now here's the distribution of sample means of size 30. So let me take a look at something. Here's what this data looks like. So here's a random sample. Here are the 10 different length of 10 different names, length of letters of the last name, and then here's the sample mean. Here's a different sample mean, et cetera, et cetera, et cetera. And now I have 1,000 of them. And I can do the same thing for size 30. Here are the sample means of size 30, and then size 100. Here are the sample means of size 100. Basically, here's a sample of size 100, and I can generate that sample mean. So now these distributions are like, this is the 10,000 samples of means of size 10. And here are the 1,000 samples of sample means of size 30. Notice this is a lot closer to being normally distributed. Now, if we look at all three 1,000 sample simulations, we have the following shapes. So here are my samples of size 10, 30, and 100. Notice the shape of this one is a little skewed to the right. This one's a little bit closer to being approximately normal, and this one's fairly normal. Notice all of them are centered right around 6.2, but the standard deviations keep going down in value. So the standard deviation of the last one, samples of size 100, is the smallest in value. In fact, here is my population. So my population sample size was 57, but just imagine that to be huge. Notice the population mean, the sampling distributions of samples of different sizes, the distribution of all those means is the same as the mean of the population. The standard deviation keeps getting smaller though. So how does it keep getting smaller? So all this and the shape gets increasingly more normal. So this brings us to this idea of the central limit theorem. And this is one of the more important theorems that we're gonna need to know as we go into this next part of AP statistics. So there's three key takeaways. The mean of each sampling distribution is the same as the population mean. So if I have samples of size 10, and then I get like a huge distribution of samples of size 10, the mean of that distribution is going to be the same as the mean of the population. The standard deviation keeps getting smaller, so of my sampling distribution. So in fact, the standard deviation of the sampling distribution of samples of a certain size is the the standard deviation of the population divided by the square root of the sample size. So we know that our population has a standard deviation of 2.2. So we expect the standard deviation of the sampling distribution of samples of size 10 to be 2.2 divided by the square root of 10, which is 0.697. In our actual calculation, we got, in our actual simulation, we got 0.703, which is really close. And of course, it's not going to be perfect just because a simulation is still, there's just randomness involved. Now, the shape of a sampling distribution of a certain size gets increasingly more normal as the sample size goes up. So that's this idea. Let me bring up one second. I'm going to pause this and bring up one other key thing. Here is the Frq problem from 1998. I think this is actually like the very first question on the very first AP stat exam. So it says, consider the sampling distribution of a sample mean obtained by random sampling from an infinite population. Again, so this idea of sampling from a huge population. The population has a distribution that's highly skewed towards the larger values. So we imagine the population has a distribution that's skewed to the right. Part A, how is the mean of the sampling distribution related to the mean of the population? So, mean of sampling distribution is the same. Let me just say, instead of saying the same, let me say, is equal to the mean of the population. How is the standard deviation of the sampling distribution related to the standard deviation of the population? So the standard deviation of sampling distribution is equal to standard deviation of population divided by square root of sample size. And the last one, how is the shape of the sampling distribution affected by the sample size? As n gets large, the shape becomes increasingly more normal. So those are the three key takeaways from the central limit theorem, and we're going to start applying those in the next lesson when we start talking about confidence intervals.